Hi guys, welcome to a new video on FORDIC 2. Today we will take a look at the performance calculations that we do before every takeoff of the Embraer 195 that I specifically fly as an airline pilot here in Austria. This is the exact program that we use on real daily flights, although of course I don't think I'm allowed to show the real thing to you. So what I'm doing is I'm showing you the actual App Store version that you can just download for free in the App Store, and which is pretty cool because you can also download it and use it for yourself, play around with it if you want. The only difference to the real version that we have is that this one does not have tail numbers. We have 16 aircraft at the moment, Embraer 195, and every aircraft has its own tail number, obviously, that we have to use for every takeoff. And also in this one, we only have like 3 different airports to choose from. So it's not the real thing where you have hundreds or thousands of airports to choose from, essentially. On this one we only have like 3 airports, but the rest is exactly the same, so it's for explaining it's perfect. So first off, why do we do those performance calculations? If you are flying a single engine piston aircraft, or if you're flying a smaller aircraft, your performance calculation is on big airports with long runways would be probably nothing at all. You do have your rotation speed and your initial climb speed that you will use for takeoff, but you don't have to calculate like decision speeds, engine out safe climb speed, stuff like this that we do have to calculate on the jet aircraft, commercial jet aircraft. So it should actually be very simple taking off in a jet, because the rotation speed, the speed at which you will start to rotate the aircraft to actually take off from the runway, is pretty much only determined by the aircraft's weight. So it should be as easy as going into a table, getting the weight of the aircraft that you currently have, your takeoff mass, and then you have the speed, like rotation speed 139 or something. And actually it should be that simple, but the reason we do all those calculations is has much more to do with, is the runway long enough? This is the first real variable, but usually it actually is always pretty much long enough to the places we fly to. There are only a few airports where you really have to calculate it in order to know. But if you're going from Vienna, let's say, to Prague, where in Vienna you have a runway of around 3.5 kilometers, in Prague you have a runway of 3 kilometers, you don't really have to calculate it if it's long enough, because it will be long enough if the runway condition code, so the runway is not wet or something, or slippery. But that's something we're gonna go into in a minute. So why do we calculate it still? Well, it's actually, I think it's mandatory for airlines to calculate it, or to do some kind of proving that the runway is the correct length. Back in the days when they didn't have an electronic flight bag like this, they used to go into the actual, what is it called, some kind of folder with a lot of sheets on it with the performance numbers. Before they did have a tablet like this, they used that. But nowadays we all have those EFBs, usually it's an iPad, that you just put in to the aircraft in the cockpit. You have a fixed position for it, which is pretty cool, and then you actually use it for the calculations. So why do we have to do this? Well, it's either, is the runway actually long enough? Can we take off on this runway with a given weight, given weather conditions, which is also quite important. And the next part is the abnormal kind of questions that you have to ask yourself for every takeoff, because in aviation, it's like 90% preparation for the worst case scenario and 10% like real flying. We do a lot of briefings for missed approaches, go-arounds, for engine out procedures, for rejected takeoffs, for emergency evacuations, all those kind of stuff. But actually, statistically speaking, never happens. But we do train for it, and we take it very seriously. And we do go through it with the briefing for every takeoff that we do. So, and here it's the same. The most important numbers we calculate on here is at what speed can we still reject the takeoff, and where it is still safe to actually stop on the runway. This is the first thing we calculate. The second thing is if we have an engine failure at the worst possible time, being right after the speed, you can still decide to reject the takeoff, which is V1. Are you actually able to climb out safely above all obstacles and fly the engine out procedure? We go into much detail about this later, but specifically speaking, these are the two things that we need to calculate for, because if we know those two things wouldn't happen, and we know the runway is long enough, like say 3 kilometers, we know for a fact the runway is long enough with good weather conditions and an aircraft like this, then we just have to look in the table, what is the rotation speed for that weight. That actually, this is the kind of thing you do in a single engine piston. But the thing that we do, apart from that, is also look at the engine out performance and look at the performance in case of rejected takeoff. So let's actually start and look into the EFB. 2, 3, there we go, screen recording. And this is the actual aircraft performance app for the Embraer. Airbus has its specific version, Boeing has its specific version for the 767, for the 777, for every different aircraft, and we use that one. This is the ePerf. You can download it, as I said, in App Store. Link is down in the description below if you want to play around with it. It's not too interesting, but I know you guys are interested in that kind of operational stuff, so I'm just going through with you now. So first off, we have the airport selection. First off, let's go to the actual aircraft. So usually before we do any kind of takeoff or landing, we would select a tail number. As I said, we have in our aircraft we have 16 in our fleet. We have 16 different tail numbers. In this case, we only have like 2 to choose from. That doesn't really matter. So you can also select the MEL. MEL. Does it work? It does actually work. You can, for instance, if you're flying around with an aircraft all day that has a thrust reverser problem, you can select thrust reverser system, and let's say the reverser 1 of the left-hand engine is inoperative. You can select that, which is pretty cool. And then you have the MEL for the whole day. If you're flying like 4 legs with the aircraft, 4 flights, you do not have to put it into the actual program every time you do a takeoff. So now you have the information. MEL items is a thrust reverser system, and this will also restrict you with your takeoff performance, as when you're doing rejected takeoff, you will have less thrust reverser available. So let's go to the city. I don't know actually those places, but let's just go full length for now. Or let's actually select full length and also Bravo 3. What this is, we have selected the runway from which we want to take off from, and then you have a list of intersections, runway intersections. Runway intersections is basically another way to get onto the runway, apart from the longest way to get onto the runway. So we just select Bravo 3. Why do you want to do that? Do you not always want to have the longest available runway to use? Well, yes, but sometimes you want to make up some delay. Sometimes it's a convenient way, and sometimes it's actually more than enough. So with our aircraft, we do not need 3.5 kilometers of runway length. We can also take off from 2 kilometers of runway length. So why not take an intersection of like 2.7 kilometers? Of course, you will have less margin, but you still have enough margin for all the legal margins that you need. And actually, Bravo 3, I would personally not choose that, probably, because it's a real big reduction, and you have to make a good point in court when there's some kind of accident happening, and they ask you, why didn't you choose the longest runway length? And we always have to kind of think in that kind of way. And also, of course, safety is a highest priority. There's a good saying in aviation, in commercial aviation, that as safe as commercially possible. So that means that, of course, it would be safer to have 4 engines on an aircraft, because if you have one engine failed, you wouldn't even like notice it too much in cruise. But And 2 engines is just much more economically feasible. So this is why we do it. And it's always how safe do I want to be, but also we want to be in time. Of course, safety is a highest priority, as I already said, but you always want to be in time. So you can like take a 30-minute briefing before every takeoff. Sometimes you have to hurry. We always do our briefings the exact way they should be, but yeah, it's just this is a really personal preference, an airline preference. I see Ryanair in Vienna always take a Bravo 4 intersection for takeoff on runway 16, and we will not. We don't do that. It's just a company mindset. It's just it's not like it's unsafe or something. There's not more crashes happening with Ryanair than it is with my airline, but it's just something to think about. So this is the runway intersection. We take multiple intersections for that for today because we want to see how differently the program will calculate our flex temperature and all of that. And actually, the Embraer is very specific and very interesting in that regard, is that we don't only have a flex temperature like in the Airbus, we only have a thrust mode. We'll go into that in detail in a minute. So runway is dry or wet. With our program, we do have more to choose from. We also have a condition code of 6 different parameters. 6 is dry, good. 6 is dry, and 5 is good. And below that, we have a different kinds of condition codes like slippery and snow, compacted snow, how many millimeters, and it's all the information is all given in the ATIS, in the Aerodrome Terminal Information Service, and we then put the information. Sometimes also with a matrix that we have in the quick reference handbook, put it into the ePerf to calculate the takeoff performance. So we just go wait for the time. Let's say we have no wind at all. When the wind is variable, you put in the worst possible wind. So there we have 3-5 is our takeoff direction. Let's say it's variable 5 knots. You would put in a wind from 170 at 5 knots. Let's just do that for the time. Let's say we have 5 degrees and QNH from 1016. Takeoff weight, what kind of aircraft is that? Kilograms, let's say 45 tons. CG is 20, and let's just press run for the time. And then we have our takeoff parameters. The max takeoff mass is 52.290. I think that's actually a E2 variant of the Embraer. It is actually, yeah. And you have various different options to choose from the left here, and we will go into that in a minute. But let's just look at the matrix that we at the takeoff card. So there you have the runway info, how much length is available with all the intersections here on the right-hand side, and down below you have the results card that you will actually use to put into the MCDU, into the thrust setting page of the MCDU. You have the thrust mode takeoff 1 at the time. You have 5 degrees of temperature and all of that stuff. They put the stabilizer trim in, and you have the V-speeds calculated. And actually, right in the bottom corner of the results card, you will see the ASD. This is the accelerated stop distance, and this really gives us an idea of what kind of stop margin we will be having in case of a rejected takeoff. So it's quite interesting. Look at that for a moment. This is something I've talked to many pilots across my company, and I don't really get why that is, but it's the same with our ePerf calculation program as well. You see here in the top hand results card for the V1 speed, you have 130. Down below is VR, which is 140. So let's say you have an engine fire at 135 knots, which is above your V1 speed, so you have to continue to take off roll. You have to take that engine fire, go up in the air, do a holding pattern, do your checklist work, be back on the ground, let's say in 10 minutes. Let's say your engine is still burning, so you have a really big issue here, a really big risk taking it up in the air. But you have to do that because you calculated the V1 speed, and as you might see in a lot of YouTube videos from takeoffs of passenger aircraft, the captain places his hand on the throttle and the thrust lever, and when the co-pilot the captain calls out V1. He removes the hand from the thrust lever, and therefore he is removing himself from the decision of making a rejected takeoff, because you need, in order to do a rejected takeoff, the only thing you basically need to do is retard the thrust levers to idle, push off the auto throttle, and then go into max reverse. The auto brake will kick on, the spoilers will kick on, and your reverse thrust will kick on. So this is how a rejected takeoff is basically done. And with removing the hand above V1, you will not do a rejected takeoff anymore. But actually, look at the accelerated stop distance. We have 3,300 meters at the top here, runway 35 info available. We have 3,300 meters available, and stopping at V1 at the max speed that we can still stop, we have a margin of around 500 meters. So my question is, and I don't really get it, why this program is calculating it that way. I've talked to many pilots. I don't actually know why that is. We could still maybe increase the decision speed to the rotation speed, which is 141. We could say V1 is 141, VR is 141, and we will probably, I don't know it, but we will probably still have a margin of around 100 meters. So why are we not minimizing that margin? But with minimizing the margin, we have a higher chance of having an engine fire during takeoff roll while still being on the ground, which is a huge thing, because if you might remember, I mean, engine fire might not be so critical as you might think. But let's say you have a cockpit fire after V1, probably the worst thing that can happen. I mean, I don't think it has ever happened before, but it could have a cockpit fire after V1. And I think from statistics, we know that if you have a fire, you have to be on the ground in 13 minutes. And 13 minutes is not a lot for doing checklist work, for doing all that stuff. So it would be much safer to reduce the margin, that's my thought, to still be on the ground. But I don't know where it actually is. I think with the Airbus calculation software, they do have a different kind of option to do that. But with our Embraer software, that option is not given. If you have, let's say we are dry, let's put it dry, then V1 is higher. You see 137, but I still don't get it. We have a stop margin of almost 1 kilometer. Why is V1 not the same as rotation speed? Why is there a difference if we have that big of a margin? I don't know if you get me, but if you know the reason behind that, or if you have a different experience, please write it down in the comments below. I will be interested in knowing. So that's that. Let's actually go to the configuration mode, which is quite interesting. Look at all the configurations that an Embraer ePerf program has. We have thrust mode. Thrust mode is the first step in reducing the takeoff thrust. It's basically as easy as, let's say, takeoff 1 is 92% N1, takeoff 2 is 90% N1, and takeoff 3 is 88% N1. It's not the real numbers, but let's just put it like this. And then you have on top of the D rate, that you actually call D rate on a Boeing aircraft, you have the flex temperature that you can additionally put into that. And the whole reason for that is to even more reduce the takeoff thrust, even more decrease engine wear. It actually does not decrease fuel consumption, but it decreases engine wear and noise. And noise is a big thing for aircraft, because we do pay landing fees depending on how noisy our aircraft is. The A320neo that we recently acquired here on my airline is flying to destinations primarily like Amsterdam and London, not because you save so much fuel, because it will be much more logical to send that aircraft to longer routes like Tenerife or Iceland, but actually because you save so much money on landing fee. This is why you need those neo aircrafts, and this is also why you do flex takeoffs, and also to do engine wear, because the higher the temperature is, the higher the exhaust gas temperature is, or the internal turbine temperature, the higher the wear of the engine. So this is how you can reduce even more your engine thrust. ATTCS is the automatic thrust compensation mode. I don't know what it exactly is called, but actually on takeoff 1 you cannot select it, and on takeoff 2 you can. The reason behind is takeoff 3 obviously as well. And the reason behind that is actually quite simple. Takeoff 1 is to full thrust that you can actually put out of the engine. So let's say you have a takeoff 3 takeoff, you flex with some kind of temperature, let's say, there it is, 31 degrees. Then you have a wind shear, you want to have the max possible power as that is available. You put the throttle to the max, and all you will get is, if you have ATTCS turned on, is actually takeoff 2. Fun fact. The instructors that I had explained it to me like, you are buying that engine, that specific engine during your thrust calculation, the takeoff calculation. You're buying that engine and you will have that for the rest of your flight. So if you know that there is wind shear, well, we do have it to do a dogo takeoff anyway, but if there's some kind of windy conditions or some kind of reason to might be needing, in any case, that full thrust, you would have to select at least takeoff 2, because in takeoff 2 you'd still have ATTCS, and that will give you takeoff 1 in case you need max power. So that's that. And the ATTCS function is also there for if you have an engine failure. It will automatically give you reserve thrust. This is also different to Airbus aircraft. Airbus aircraft will usually have a high acceleration than Embraer aircraft. Maybe one reason is because they are more powerful, but another reason is that actually Airbus aircraft do flex in a different kind of way. At least that's from my knowledge, because they do not need to increase thrust in case of an engine failure. Our aircraft flexes so high that in an engine failure the thrust wouldn't be sufficient. So the first call out during an engine failure is engine failure. The pilot flying calls check thrust, and what the pilot monitoring then does is go onto the ICAS screen with the N1 indication and check if there is actually reserve thrust displayed. And if that's the case, ATTCS has worked, and we can be sure that thrust is sufficient for the engine out procedure. We'll go into that in a few minutes. And if the thrust is not sufficient, if the reserve thrust did not turn on for any specific reason, it is the pilot monitoring's duty to push the thrust levers to the max detent, which will then give you either, if you selected takeoff 3, takeoff 2, or if you selected takeoff 2, takeoff 1. So, fun fact, even during an engine failure, we do not go full throttle. We only go a pre-calculated N1 target that is sufficient for the whole engine fail procedure. Ref ECS is just environmental control system. If you turn that off, the bleeds will turn off for the takeoff, and that will give you a little discomfort, because the bleed will kick in once there is climb thrust set, and then it will push really good air into the fuselage, and it's kind of hard on your eyes, so we do not take that off at any time. What you can also do is leave the APU on, and then from the APU logic, APU will power the air conditioning unit if that is turned off. Down below is Ref AI. With the procedures is that if there is visible moisture, like rain or fog or any clouds below 1,700 feet above ground level, you will turn from 5 to 10 degrees, you will turn engine on, and from below 5 degrees, you will turn all on. All is wing, the wing leading edge of both wings from the engine out towards the wingtips will be heated, and engine is of course the engine heating. The inlet of the engine will then be heated. And above 1,700 feet, the automatic logic of the Embraer takes over, which means that if it senses ice conditions, it has a sensor, then it will automatically kick on the the de-icing of the aircraft, or the anti-icing. It's an anti-icing. Flex takeoff is straightforward. I think if you probably watch my channel, you do know what flex takeoff is. It's the second way on the Embraer to reduce the takeoff thrust. Again, why you want to do that? To save engine wear and noise. Auto brake RTO, you can also have a manual release where the auto brake doesn't work, so you might turn that on or off. But usually it's set to RTO. If you have the auto brake not working, you have to do manual braking in case of an engine failure. My guess is if you have in case of a rejected takeoff, my guess is if you have a rejected takeoff, you will probably very soon be applying manual brakes, because usually on normal runways, you would have a lot of distance to stop the actual aircraft. Let's say you have an engine failure at 100 knots and you do a rejected takeoff, probably will be soon kicking in the brakes because the deceleration of the aircraft will be tremendous. You will have never felt something like that. It will be tremendous. I tell you that much. CG envelope, I don't know actually what that is, because we do not have that in our program, and I've never talked about that. Yeah, that's that. You have the takeoff weight, obviously. And now something interesting. We earlier talked about the takeoff intersection. We do not have two takeoff intersections, Bravo 3 and the full length. Let's actually go to Bravo 3 for a moment, and we see that the flex temperature here in this case it's takeoff 2, flex temperature 47, and in this case we have takeoff 2, flex temperature 36. We flex higher with the full length available, and with the lower length available we will flex at a lower setting. And there's actually only so much temperature of where you are allowed to flex your engine to, so this is why we have the thrust mode setting as well, sort of for the confusion here. You also see that you are field length limited. This is the maximum structural takeoff weight of the Embraer, like E2 variant, probably 52 tons. And if you scroll to the right, we have the field length limited, all engine inoperative. We're here field length limited here with the performance limitations with Bravo 3, which only gives us 2,100 meters of takeoff run available. And down below we see our accelerated stop distance, and we only have like 5 meters of stop distance available. So there I get it that V1 is reduced from VR because stop distance is so little in this case. But if we want to increase our stop distance, we can switch flex off, we can put in takeoff 1, and then we have a stop distance of, you see, 500 meters again. But of course this will be quite bad for the engine because we're going full power here. But in case you need it, you have those options, obviously. So let's talk about the engine out procedure here. Engine out procedure has to be incorporated by the operator of the aircraft, and they have to, for every airport they fly to, they have to calculate kind of a instrument departure that will ensure that if you have an engine failure, you will still meet the obstacle clearances that you need during an engine failure, which are actually quite slim, but you still have to do, of course, get over all the houses, over all the trees, over all the mountains with an engine failure. So this is what the engine out procedure is. And usually when there is just flat land, and today I'm in Prague actually, on a layover in Prague, and when there is flat land all around, and the mountains are quite low, you usually have a very easy engine out procedure. Today in Prague I think it's something like just straight ahead, and then about 15 nautical miles at the end, away from the airport, just straight ahead, go into the holding pattern at this waypoint. So we put that in the fixed info page, and that's it. And this program also calculates if you actually make the whole engine out procedure in case an engine fails. Very important, of course, as well. This is a big thing why we calculate all takeoffs, is to know with two engines we can depart from anywhere, really. We have so much excess power, but with one engine we have to do the engine out procedure, and we will calculate the whole thing if that's actually possible to do. So that's that. I think that's pretty much it. We talked about everything. This is a program we use in real life. Again, I do have a different program here actually for our operation. This is just a free tool that you can actually download and play around with as well. If you have any more questions or my recommendations, put it down in the comments below. I would be happy to read them. And see you on the next video, probably a flight sim video. So see you then.